just some little algebra out here. That's going to be the J prime and the J double prime, and the J prime plus J double prime plus J prime. I'm extremely prone to errors, so make sure that I'm doing it right. You don't think of everything I'm writing up there. So of course this comes off as J prime minus J double prime, and what I will have is J prime plus J double prime plus 1. And this is going to be the equation I really want to use. That's the equation that gives me the transition frequencies for every possible transition that we sort of wrote up from there. Let me write that out here. Now this is my general equation. Now if I want to reduce this to see what happens for the red line that we saw for the R branch and the purple line which is for the P branch. For the R branch, what is my selection group? So if I now throw this into this equation, I'm going to get my actual transition frequencies for the R branch lines. And what is delta J going to be? That's basically what it is, and therefore it also means that that's going to be J prime equals J double prime plus 1. So now let me take this fellow and talk about it for the R branch. What is this for the R branch? 1. So no worry. Here I want to put J prime as J double prime plus 1, which is what it is from that. And after that, I have another J double prime plus 1. Therefore, I'm going to get 2J double prime plus 2. So if I take this 2 out, for the R branch, I know how to get the frequency. All I have to do is to use that equation where J double prime is going to be my lower state quantum number. So 0 to 1, 1 to 2, 2 to 3, 3 to 4. All I do is throw in my lower state number. I know what B is. This is of course a combination of some bunch of frequencies and the anharmonicity constants. So if I have all of this, I can actually tell you what the rotational line frequencies would be for every line in the R branch. You can go back and do this for the P branch. What is the selection rule for the P branch? So delta J equals minus 1. I'm not going to bore you by doing all this again. For the P branch, it's going to be minus 2B. You will get that. But keep in mind, it's not J prime. Just to get the form right, you could have written the whole thing in J double prime also. But just to get the form similar, I've used J prime in this case and J double prime in this case. I've reduced it to J prime in this case. I've reduced it to J double prime in this case and J prime in this case. I can now write a very general equation for these lines in the rotational bidirectional spectrum. And what is the general equation going to be? It's going to be delta mu R or P M, where M is J prime plus 1 for the R branch, and M is minus of, where M is J double prime plus 1 for the R branch, and for the P branch, M is going to be minus of J prime plus 1. So I'm giving you a general equation where M takes on different values depending on whether you're looking at a P branch or an R branch. So this is basically your working equation to calculate all the lines of a rotational spectrum. And this for rotational spectroscopy we use if they have to just simulate the entire spectrum. If they know B, they know omegas, and they can go back and calculate what the spectrum would look like. Of course, we need the intensities also for simulation. But you can always, you know the energies, you can calculate population, and therefore you know the intensities also. In fact, if you like programming, maybe you should just try simulating an HCl spectrum for itself. All you have to do is use an equation of this sort, get the omega E for HCl, omega E XC for HCl, get the B values, calculate the populations, therefore you know the intensities. Use this equation for getting the line positions, and therefore you can go back and simulate what the spectrum should look like. Not too difficult to do. So in fact, might be a good exercise when you record the HCl spectrum experimentally to go back and do the simulation and see whether you can match up these two as well as you possibly can. We saw the case of HCl that you have this nice hump because the most probable J always is going to dominate the intensity of the transition. So we saw that the lines were doing this on one side and doing this on the other. Strictly speaking, the one that has the greatest population, let's say if J4 has the greatest population, then in the R branch, what is that going to do? It's going to give you a 4 to 5 transition. That should be the strongest. In the case of the P branch, what should that be? 4 to 3 branch, that should be the strongest. So you know straight away. You have sort of a cross check. But of course, as I said, you want to make sure that your instrument is responding the same in both regions of the wavelength for the same amount of light falling on it. And that need not always be the same. So you'll have to make corrections, calibrate your machine with respect to instrument response, and then make this the final. But this sort of a spectrum you will get only if your machine has enough resolution, meaning if it can see each line individually. If your machine has very poor resolution, what do you think you will see? You will not see this. Something like this. The individual lines out here have all sort of got jumbled out because the machine does not have the resolution. What do I mean by resolution? If there are two lines separated by, let us say, two wave numbers, and my machine has a resolution of, let us say, 0.5, meaning anything within 0.5, just beyond 0.5, the machine can actually flag it as two separate lines. That's what is called as resolution. But if the machine is very poor resolution, low resolution machine, then it might not be able to tell between two lines unless the two lines are like 10 wave numbers apart. Whereas here, the lines are like few wave numbers apart. Therefore, it is quite likely that you will not have a resolution in some cases to see individual lines, and all you will see is a mixture of all of these, and you get this. Is this useful? Yes, it's still useful because you can still make sense out of this. Why? I see where I get a maximum. I see where I get a maximum over here. What is the J max going to be equal to? KT by 2HCB minus R. So whatever I see over here must belong to that J value, which is going to give me the maximum. What is the frequency of that J value in these rotational transitions? I can use this equation because if I know temperature, if I know B, maybe I don't know B, but let us say if I can calculate the J max and throw in over here, then I know at what frequency I must get the maximum J value. This J and this J must be the same. This J belongs to the R branch and this J belongs to the P branch. So all you now have to do is use this equation and knowing fully well that the J has to be equal to this, you can go back and calculate. You can measure this. So you can actually measure the spacing between the two peaks, and once you know the spacing between the two peaks, you can use this equation, which I want you to do as sort of a homework, and come back and be able to measure B from this. You don't need J because you've got 2 points basically going to give the calibration. And therefore, if you don't just tell me from an experiment, And you know that this J max will be the same as this J max, except that this J max is your J max for your R branch, and this J max is your J max for your P branch, and both are the same J's. You can therefore use this equation to find out what the spacing must be. And using the spacing, you will be able to figure out what the B value is. So even though you don't have the resolution to find two B's through which you can get the B values, by simply looking at the maximum in these speeds, you will be able to come back and say what the B values are in these experiments. Of course, Banwell has sort of explained that, so I'm not going to sit down and derive that. It's pretty straightforward. Just do it. If you have a problem, we will come back to it and look at it a little. Okay? So, what I would like to do today before we close down is the following. We made this assumption that the B values are the same in both V equal to 0 and V equal to 1. If the B values are the same in both V equal to 0 and V equal to 1, what does that mean? It simply means the way these lines are going to be, the energy levels are going to be stacked up, are going to have the same differences here as they're going to have over here. Because the first line will be 2B, then it is 4B, then it is 6B, 12B, and so on. So as long as B is the same, this set of lines and this set of lines will actually match because the B's are the same. But the question is, are the B's same in B equal to 0 and B equal to 1, or is it a pretty bad assumption really? So it's a good assumption to begin with, because we needed something simple to first analyze the spectra. But the question is it a good assignment, is it a good approximation for an eventual analysis of the data? The question therefore is that, supposing I have harmonic potential, what is B given by? Right? And what is this R going to be? It's a bond length, but then we said that R has to have some meaning in the sense that the molecule is vibrating all the time. So what R is that? Just an average R. So if I take B equal to 0 and B equal to 1, is the average value of R the same in both cases? Yes or no? Yes. How many say yes? How many say no? How many are asleep? See, this molecule is, this potential is symmetric. So this will goes as much on this side as it goes on this side. When it comes here, it goes as much, a little bit more, but again as much on one side as it is on the other side. And therefore, what do you think will happen to the average value of R all the way across? It's going to be the same. Therefore, as long as the potential is harmonic, the average value of R has to be the same in every vibrational level. Supposing the potential is anharmonic, what happens? You'll see one thing, that this level out here, the repulsive potential doesn't change a whole lot. So the repulsive potential is actually, the repulsive part of the potential over here is actually guided by nuclear repulsion. Very, very strong. Nothing much you can do about it. But what about this part of the potential that is guided by the electron overlap? Therefore, this changes quite a bit. But this doesn't change from what it was for a harmonic potential. What does that mean? V equal to 0. I go up here and back here. I'm going more on one side and not so much on the other side. When I go to V equal to 1, what happens? The situation gets worse. I actually go a little bit more on this side, but I still keep going on the other side as much as I was going for a harmonic potential. As I keep going up, further up, what happens? This is going to be dominating, this part of the potential. So what is going to happen to the average value of R as you keep going from V0 to V1 to V2, V3, V4 and so on? Average value of R has to increase. In fact, It sort of goes this way. The average value of R will increase as we go from the lower vibration levels to the higher vibration levels if the potential is anharmonic. So what should happen to my B now? If I use the R value over here and I use the R value for this, there are two different average R values, and therefore whatever I use for this and whatever I use for this is not the same. And therefore it's quite obvious if you look at the anharmonic potential that the B values have to be different for V equal to 0 and V equal to 1. So all the assumptions I made that they are the same is not really correct. In other words, the vibration is actually causing a change in the rotational constant. So my assumption that vibrations and rotations are two separate things and we don't have to worry about their coupling is wrong because the vibrations are actually changing your rotational constant. We call this the vibration rotational coupling. As we keep going, V equals 5 is going to have a very different V value than what V equals 0 would be having. V equals 10 is even worse and so on. If you're convinced with that argument, now let's go back to the harmonic oscillator argument, where we sort of pretended that the average value of R does not change, and therefore the B values, it's okay to have the B values the same all the way up. Now what I'm going to tell you is even there you are wrong. You've got harmonic oscillator potential, you are wrong. Why? What is this here actually? It is not the average value of R you should be really calculating. What you should really be calculating is the average value of 1 over R squared. That's what you should be doing, because what's occurring in this equation is not an average value of R, it's actually 1 over R squared, and it is the average value of 1 over R squared that you should be taking in all your experiments to calculate B. What happens over here in the harmonic potential? Small value of R, large value of R. When I get to V equals 1, what happens? The small value gets even smaller, the large value gets somewhat larger. And now if I try to use these two values, take the 1 over R of this, 1 over R of this, and calculate the average of those two. Do you think I'll get the same average of 1 over R squared everywhere? No, and you can actually do that, try it out. Let's say this is let's say this is 1 and this is 1.5. Let's say this is 0.9 and this is 1.6. And I'm doing it in such a way that the average should be the same. Right? But the average value of 1 over R squared, if you start to calculate for all this, you will find that the average value of 1 over R squared is not going to be the same for this as well as this, simply because this number is getting smaller and smaller. Therefore, the 1 over R squared corresponding to the smaller number will actually start to mess up your average. Therefore, even for a harmonic oscillator potential, to say that the V is the same for V equals 0 and V equals 1 is wrong. So all this while, we have been looking at something that really wasn't right. But then, we always do this to make life easy to begin with, just to understand what's going on. And then we come back and say, yeah, I know I did something wrong, but I was doing it just to get a picture. At least we have a picture. We work out the picture of a P branch, we work out the picture of an R branch, and all the information that goes with it. Now I'm going to come back and say, well, the B is not really the same, the B is somewhat different. And if the B is different, what happens to my spectrum? Small changes will occur in the spectrum, but the larger picture will still remain the same. I got the larger picture quite easily by simply assuming the B values to be the same in both states. Now I'm going to come back and say, for a harmonic oscillator potential, saying the B is not the same, being the same for all the levels is wrong. For an harmonic potential, it's definitely wrong. And now we're going to come back and see what changes these B values will offer for you as far as the spectrum is concerned. Now I'm going to say that the B value in V equal to 0 is not equal to the B value of V equal to 1. So all these spectra I drew for you this morning, in the beginning of the class, equal spacings here and the same spacing up, will not be the same. What will it be? It will be one set of spacings here and a different set of spacings over here. Therefore, you'll have to go back and redo your equations, particularly the ones we did over here. Redo it. How am I going to redo it? I'm going to say that it is B into J plus 1, or B prime into J plus 1. On the other side, it's going to be B double prime minus J prime into J double prime plus 1. I used the same B for both terms in the rotational equations. Now I have to use two different B's for those two equations. And then we have to redo the whole calculation. And you will find, if this is in general to be alright, what is really going to happen is this 2B will not show up. It will actually show up as B prime plus B double prime. And what is going to happen if B prime equals to B double prime? You will get 2B. So the limiting case will actually turn out to be what it is supposed to be. So when you go back and redo this, you will find that these equations will just sort of manifest a slightly different form, which is in keeping with the fact that the B primes are not the same in both the lower and the upper scales. We will do that in the next class, and then we will move on to other